another section on theoretical material about algorithms. So we need to look at these part, asymptotic notation, and how to measure the time, because this is a critical component of algorithms and data structure for the analysis of algorithm and data structure. And it is something that, especially asymptotic notation, it's something you need to know as a computer science student, especially those of you who will go to graduate school. So this morning is probably the most important lecture in terms of things you need to remember. It's not the most interesting or the most important in terms of what you're going to learn, but these are the things you need to remember as somebody who has studied computer science. You need to remember this for most of your life. Okay, so I will move on with the lecture. So today we will do this this section or this lecture on asymptotic notation, and if we have time, we will start basic data structure. So the things about arrays and pointers and variable, etc. So so last week we discussed about the strategy to measure the time of algorithms, and so we discussed about technique to measure the time. We first start with trying to measure the time of an algorithms by measuring the execution time of the program that implement the algorithms. And we came up with the conclusion that this is not going to work because it is going to be biased by things like the computer on which the program is running, and it will depend also on the implementation, the code that has been written to implement the algorithms. It will depend on the operating system that where we are running this this program, and it will depend also on the other applications that are running in same time as our program. So there are lots of cases that can bias the running time, so we can run the same exactly the same algorithm on two different computers and get different running time. So we conclude that this is not a good idea, right? Now we decide to scrap this, and we decide to count the number of time operation in the algorithms execute. Okay, so we say, okay, forget about the running time, the wall clock time, and we are going to count the operation that appear in the basic operation that appear in the pseudocode. Okay, so and we try to make abstraction of the exact number of machine instructions for executing each of these basic operations. So we abstract these by using some constant that represent the number of basic operation, a number of machine instruction, and then we count the number of time each instruction is executed in the pseudocode, and we came up with an expression like this one, which is the total number of operations that are executed. Notice that these basic operations are different from one another. in terms of the implementation of this operation, in terms of the machine instruction, but we abstract this using some constant in front of the number of time each operation is executed. So we came up with an expression like this, an squared plus bn plus c, and then we decide, well, there's no need to count how many times each basic instruction is executed. We are just going to count the one that is executed the most often, okay? So we came up with the idea that this while loop here, the instruction in the while loop, so the testing of the condition in the while loop, so we test whether I is greater than 0 and whether AI is greater than the key. This basic operation is the one that is going to be executed the most often, at least one more time than the instruction inside the loop. So we decide that we are going to count only one instruction, the one that is executed the most often. So we count how many times this instruction is executed. So if we look at C5, this summation here is executed for every iteration of the for loop, the outer loop. So this instruction is executed that number of time for each iteration of the for loop. So we came up with a closed form for this expression, which is C5n squared plus C5n over 2. Now, obviously, if we count only one operation rather than all the operation, we have a description of the running. It's not as precise as the one where we count all the number of, we count all the basic operation, how many times each of the basic operation is executed. It's not as precise. It is, of course, a value that is smaller than this one. It's going to be a value that is smaller than the one that corresponds to count all the basic operation. But we said it's smaller by some constant factor, okay? So if we multiply C5 by some constant, we will get to A. If we multiply C5n by some other constant, we will get B. And if we multiply minus C5 or C5 here by some constant, we will get C. So the difference between the expression that describes the whole, how many operations are executed if we count all the basic operations, and the expression that expresses the number of times the instruction that is executed the most often. So the difference between these two is just a constant. And for us, a constant is not going to be something we care about. So for example, if this is executed one more time than this one, it doesn't matter much, right? So this is just one more time, so it's a constant difference. So we do not want to bother with this kind of differences because it's going to make it impossible to actually compare algorithms with one another if we go to this level of detail. And for example, if we implement this in some other language, it might be that it might be that the total number of operations is going to be different if we implement this in another way. Okay, so counting the total number of operations, number of basic operations, if we implement this differently, there are many ways to implement this actually. So it's going to be different. And this also is going to be a problem. This expression that represents the number of times the instruction that is executed most often, it's also going to be a problem because depending on the implementation, this expression may change also. So we are going to get rid of this expression as well by keeping only the dominant term of the polynomial that express the running time, the number of times the instruction that is executed most often. So now how many times this instruction is executed. We are going to get rid of the constant, So you already know we don't care about the constant, so we don't care that this is the constant smaller than this one. So if we multiply this by one constant, we will get this. We already don't care about this. And now we have this constant here. Why do we care about them? So why do we care about C5 and 2? They are constant also, so we can get rid of them. And we also get rid of all the other terms in n that are smaller than the dominant term. So for this moment, maybe it's not very clear for you why we want to get rid of the other terms, but you will see when we study the asymptotic notation why we do this. Okay, so we conclude that we can represent the running time of an algorithms by just keeping the dominant term of the expression that describe how many times the basic instruction that is executed the most often, how many times this instruction is executed. So we came up with some kind of expression, some kind of polynomial, and we now going to remove all the terms of this polynomial, just keep the dominant term, and then remove all the constant as well, and say this is the running time of the algorithm. So n squared is the running time of the algorithm. So we are going to do this when we analyze the running time of algorithms. We are always going to do this, use this approach. Okay. We first count how many times, we first select the instruction that is executed the most often, and then we count how many times it is executed. We come up with some polynomial that describe this running time, and then we remove everything in the polynomial except the expression that represents the dominant term. Okay, this is a polynomial in n, so we just keep the largest term in the polynomial, get rid of all the constant. So this is the procedure we're going to use, and this is the procedure that is used in all algorithm books or papers when they analyze the running time of algorithm. We do this also when we want to measure the amount of space that a data structure is taking, but in this class, we are not going to care about the space. We're not going to try to measure the space occupied by data structure. Okay, so, and finally we arrive with we call this expression that only have a dominant term, we call them orders, because they are going to represent the amount of number of times the basic operation is executed as the input size increase. Okay, so n represent the input size, and n squared represent the number of time one instruction is executed. So this represents by how much the running time increase when we increase the input of the algorithms, the data. So this is called the rate of growth or order of growth, and there are some dominant terms that are so common in algorithms that we give them give a name to these algorithms that have this kind of dominant term. So if the dominant term is log n, then we say that these algorithms, all the algorithms in log n, they are running in logarithmic time. Okay, and normally this is good. So if we have an algorithms that for which the running time grow by log n in terms of the input size, this is considered to be a good algorithm. This is considered an algorithm that is not taking too much time to solve a problem. Another one that is very common is linear. So linear means that the number of basic operation execute number of times the basic operation that we count is execute is some factor, some constant, the input size. Okay, so C here represent some constant time of the input. Okay, and this C is going to be abstract by the asymptotic notation. So the asymptotic notation means that an algorithm is running C, when we use big O, for example, is running in order of some C of n. Okay, C is not important here, but not important. It is going to represent the actual running time of the algorithms, but we're going to abstract this. Okay, so all the algorithms that running in order of n, they may have different C in front of it, but they are equivalent. Quadratic is the same idea. So it means that the number of times the instruction we count is execute is n squared, grow by a factor of a quadratic factor. Okay, in terms of the input. So we call these functions that have this complexity, this running time, that have a complexity that is quadratic in the input. And finally, we have other orders like cubics. That's for those algorithms that for which the running time increase in cubic time with respect to the input. And then we have a general term that describe all these guys, linear, quadratic, and cubic, and we call it polynomial. Polynomial means that we refer to the exponent here of the dominant term in general. Okay, so we abstract the exponent. So we say that an algorithm is running in polynomial time if the exponent is one of the value from 1 to whatever. Okay, and so polynomial is a general term that describe all these functions that have a cubic, quadratic, linear, or n to the 4, n to the 5. This is not in this class, but if you are doing a class in a more advanced class or something related to complexity theory, this will become a very important concept in that context, but here it's not very important. Except to say that if an algorithm is running in polynomial time, it's considered to be good compared to those who are running an exponential amount of time. So exponential amount of time means that the time grow some exponent of constant k in term of n. Okay. So you know that exponential function grow very quickly. So if we have the running time that is growing at that speed, that's not a good algorithm. But unfortunately, many algorithms that we use in practice have this complexity, this running time, and we do not know. They are solving some problem, and we don't know a better algorithm than these to solve the problem. So there are many problems in engineering or business for which the best algorithm we know to solve them has this kind of running time, exponential running time. And it will be a great discovery if anybody was able to discover a polynomial time algorithm for this problem for which we don't know any polynomial time algorithm so far. So it will be a huge achievement. So many people already tried this, and so far in 50 years, we have not been able to break this kind of border. So so we have those asymptotic notation, big O, gamma, and theta. So what is the big O stand in front of the log m? Okay, so we have a running time that is growing using this function, so growing in log time of n. So growing slower than n. So why do we put the big O in front of it? So the big O has to have one important meaning is that it said that we are bounding the running time of the algorithm with this function. It has another meaning, and so big O, omega, and theta have different meanings in terms of how they bound the running time of an algorithm. So we already described this. This bound, this is an upper bound, this is a lower bound, and this is an exact bound. So these expressions, these notation have this signification. But they also have another meaning, all of them. It means that there exists some C, okay? So the big O stands for C in front of log n, such that the function that is bound by log n is the growing time of this function is smaller than C log n. We don't know the C, okay? But there exists a C such that the function that we bound is smaller than this. So for example, let's take n square. So what does it mean, big O of n square? So this is my bounding function. It means that, for example, my function, my running time, if I have a running time that is n log n, it means that this is smaller than n square multiplied by some constant c, okay? So if n is equal to 1, for example, n log n is greater than n square, right? If n is equal to 1. But if I plug a c in front of it, I can make it smaller. I can make n log n smaller than this, okay? So the big O, or the omega and the theta, they are an abstraction of a constant that is there in front of the bounding function, to means that I can find a C that will make this bounding function bigger than this one for some value of n that we call n0 and larger. So after some value of n, this thing here multiplied by C is always going to be bigger than the function that I'm bounding. So those notation have two meanings: upper bound, lower bound, exact bound, and also they means that they stand for some constant. Okay, so that's why we have these constant here when we describe this order. Logarithmic means that we have a function that is bound by this multiplied by c. So there exists a c such that my other function is smaller than this one. The same thing for cn, cn square, and all those things. So the constant c is in practice, okay, I can find a real constant such that this is going to be larger than another function as n tend toward infinity. So I will describe these three notation here and try to make them more clear. And we will do some exercise to practice to prove that we have found a bounding function for any polynomial that describes the running time of an algorithm, given algorithms. So here fn is going to be a polynomial that describes the running time, okay, of an algorithms, and gn is the bounding function, okay. So we are going to say that gn here, order of gn, is a class or a set of function of polynomial such that this polynomial can be bound above by gn, okay, so such that fn is smaller than gn if I multiply gn by some constant c, and for some value of n that is greater than n0. So past n0, for all of the value of n, we will have that fn is dominated by gn. So this set representation of the complexity, the big O complexity class, is just saying what it describes here. big O Gn is a class, is a set of all the function, all the polynomial that represent a running time of algorithm that can be bound above by this function. So as I said last week, we can find easily a GN that can contain all the polynomial function. For example, I take GN that is exponential, and it's going to include all the polynomials. So, but this kind of upper bounding is not very useful. So usually we try to find a GN that is as close as possible of one. If we try to prove that some function fn is in order of Gn, we try to find a Gn that is as close as possible to fn, so that we can bound very accurately the running time of functions, so that it is useful to compare the running time of a function of an algorithm with the running time of other algorithms. So we try to find a function, the bounding function, that is very close to this one, for the reason I have just described, so that we can compare algorithm, running time of algorithm with one another's. So graphically, it looks like that. So this is the function Gn, and this is the function Fn. So the n0 is some value of n, beyond which, if I multiply Gn by some constant c, Fn, the running time of the algorithm represented by this polynomial, is smaller than Gn. By the way, we try to find a Gn that is just one term. I have only one term, as to make the things more simple to compare, to make the thing more simple, and also to be able to classify the bounding time in this class that we have just described. Okay, so we try to use a term, we try to use a function Gn that is a simple, has only one term, so that we can represent the bounding function in terms of this order, grow rate order. Okay. So we have Fn that is in omega of Gn. If Fn, if the running time of the algorithms that have this polynomial expression, if Fn is smaller than Cgn for some value of C greater than 0, and some value of n0 that beyond which Gn is greater than Fn. So this is the meaning of Fn is omega of Gn. Some people write Fn is equal to big O of Gn. It has the same meaning. It means that Fn is in this set or in this class, but I prefer to use this form to mean that this is really in that set. Okay, so we start with a first example. So Fn here is again a polynomial that represents the running time of one basic instruction in an algorithm. Okay, so one basic instruction is executed that amount of time. So 27n squared plus 355 over 113n plus 12. Okay, so this is just the running time, or the number of time one basic operation is executed, and we assume that that basic instruction is the one that is executed the most often. And now we want to know in which class we can put this algorithm. Okay, we can put the running time of this algorithm. So I have to find a Gn that is going to bound this function, this expression. Okay, and here I'm going to select a Gn that has only one term, and the Gn is n squared. So obviously n squared is not bigger than this, okay, right away, right? But we can make n squared bigger than this if we put a constant in front of n squared large enough so that this gn is going to be greater than this expression for some value of n greater than n0. So here what we do is we calculate that constant in front of n squared. So we try to simply add all the constant of this expression together, and then we put this in front of n squared. Obviously, n squared is greater than this, so if I put a constant in front of n squared that is greater than this constant, that term is bigger than this one, and any constant of n squared that is bigger than 12 also make this term bigger than this one. So essentially what we do here is look for that constant c such that my bounding function gn is going to be larger than this expression. So we sum all the constant together and we arrive to this thing here. So this is my c, and for any value of n starting with 1, gn is greater than this. So when we want to finding a function that is bounding fn is not actually very difficult. We just need to find that dominant term. But then we need to find a proof that we are correct. So the proof consists to exhibit a c for which this thing is smaller than f. This expression is smaller than my bounding function. So we need to find that c, and we also need to find n0. So beyond n0, for all value of n up to infinity, we have to have gn or n squared greater than this expression. So one way to actually find one way to prove this is just to find a constant c that is large enough to plug in front of n squared. Now we are going to look at one more technique, I think, to prove the bounding function, that we have found a bounding function, and also describe other situations that will occur, other type of polynomial expression or expression that describe the running time that may occur when we try to measure the number of times the basic operation is executed. So here I have a running time that is tn n squared, 3n squared plus 2n. So this is the running time of an algorithm. And I want to discover the growth rate of that function. So I want to discover in which class I'm going to put this function so that this class represent the complexity of this function. So we can one thing we can do is get rid of all the constants. So when we are looking for gn, right? So I'm looking for the dominant term. So and I said dominant term is always going to work. So we get rid of all the constant, and then we get rid of the other term in the function that describes the running time. This also applies for running time that have this form. Okay, so if I have a running time that is 2n plus 1, this is actually equivalent to 2 times 2n. So so it's a constant in front of 2n. So that means that 2n plus 1 is actually can be bound by 2n, because again I can rewrite this expression as 2 times 2n. And this expression is a constant in front of the dominant term. So one strategy to find the Gn is to get rid of all those constants. So I get rid of this constant, I'm left with this. And this is going to be, 2n is going to be my Gn here for this kind of running time. We may also have running time that are expressed in different logs. Okay. Let me do something for my cough. Okay, so we may have the running time that is using different logs, so log with different base. The difference between two logs that have different base is just a multiplicative constant also. So if we have a log in base b of n, we can express this into another base, a, just by multiplying log a times c. So the difference between two log or log that have two different base is just a multiplicative constant. Thus, we don't care about these kind of difference. The same reason as we don't care about the fact that 2n plus 1 is equal to 2 times 2n. So the difference between these two terms is just a multiplicative constant. So we don't care about these differences. And we don't care about which base a log is when we measure the running time of an algorithm. So we are not going to bother with the base of the log that represent the running time. And we are all going to assume that the base is 2. So when we discuss about running time that are some log, we are going to assume that is log in base 2. And if the log of the running time of the algorithms is not in base 2, we don't care. We can still write the bounding function, the Gn function, in base 2, knowing that there exists some constant that can be multiplied in front of the 2 to get to a base 10, for example. Okay, so log in base 2 is equal to log in base 10 if we multiply base 2 by some constant c. So once the running time of an algorithm has been simplified, we take the fastest growing terms, and this becomes our Gn. So for finding the Gn of this running time, we again eliminate the constant, we eliminate the smaller term, and we get this thing here. So this is how to find the dominant term. Okay. Now we need to prove that this is really a bounding function. So we need to find a constant c and a value of n for which beyond which the function fn is dominated by Gn. So you agree with me that these two expressions are not the same, right? So n squared and these two things are two different functions. So this is a function and this is another one. So that we have extract from the running time of the algorithm. So these are two different functions. But we want to use this one to bound the other one. And we can do that if I can find a constant c that is large enough such that n squared is going to be larger than this. Okay, so to prove that a function fn is in some order Gn, we need to exhibit the constant c and a value of n0 such that as the running time grow, as the input grow, the running time of the algorithm is always smaller than the function Gn. So the number of operations executed by the function Gn. So as you know, this is running time is this is a running time of an algorithms that have an input of size n. We know that the running time of the algorithm is going to increase as n increase, okay, and is going to increase by this amount, okay. So if n doubles, so this is going to be the running time will be n times n for that part, multiplied by 5 plus 3n. So if n doubles, so it's going to be 2n times 2n plus 3 2n plus 20. So as we double the number, the size of the input, the running time is going to increase in the way I have just described. So this is the running time that is increasing in terms of the input size. And I want to put this running time smaller than my bounding function. So I want this guy to be smaller than my bounding function. And I want to prove that actually this running time is going to be smaller than my bounding function for some c and some n0, beyond which the running time of this is always going to be smaller than the running time of the bounding function. So we can use the trick that we have described previously, pick c to be the sum of the constant of the running time of the algorithm of Fn. And then, of course, if I do this by the same argument that I gave previously, so if I put 28 in front of n squared, this is going to be definitely larger than this, and definitely larger than this, because these two terms are smaller than this one. So if I put 28 in front of n squared, this thing here is going to be smaller. So one easy way to prove that we have found a bounding function for this algorithm, for this expression, is to find a constant that is equal, find a constant c that is equal to the sum of the constant in the polynomial fn. If we do that, then n0 is easy to find. N0 is equal to 1. Okay. So again, if I have this thing here, and I substitute this by 5n squared plus, yeah, here we'll have a new expression that will be that will be 28n squared. Okay, so I'm not going to try to explain it this way. It's maybe more confusing. Oh, here it is. Okay. So since this is the dominant term, 5n squared, so if I plug the dominant term in place of these terms here, so n squared for in front of 3 and n squared in front of 20, all these guys summed together are equal to 28. Okay. But we already know that this term is bigger than this one. And very obviously, this one is bigger than this one. So this expression, which is 28n squared, is definitely greater than this one for all value of n, starting with n equal to 1. Okay, so if we substitute in this expression n squared everywhere, so that gives us 28n squared. And this is bigger than this one, because again, we put two new terms here that are bigger than this one, so this is smaller. Another way to prove that we have found a bounding function on an expression that describes the running time of an algorithm is to guess value for c, and then try to find the n0 that will work. Okay, so if I put c smaller, you will see this when you do exercise. If we put the c smaller than what we got here, The consequence this will have is that I need to increase the value of n, the value of n0. So we can play with this with c, put it c smaller than the sum of the constant. But if we do this, we need to find an n0 that is going to work. So for this way to prove this relation, Fn is in order of Gn. Prove this is true for a particular, for a special expression. We need to apply some algebra. So here I assume that C is going to be equal to 1, and I need to find my n0. So if I fix C to be some specific value, then I need to discover for which n0 that function is going to be smaller than Gn. So here I have another function, another running time example, and my bounding function is n squared. So I want to show this true. Okay, so I want to prove that this function is really dominated by this one for some value of n greater than n0. So for doing that, I need to discover the two constant c and n0. I already decided that c is going to be equal to 1. So then I need to discover what's going to be n0. So sorry. So I need to make this thing here smaller than n squared, knowing that c is going to be equal to 1. So we need to do some algebra. So we will get rid of this term here. So transit it to on the other side. And I now just need to guess for which value of n this expression is going to be smaller than this one. 3n is going to be smaller than 1 over 2 n squared. And this is going to work for 6. So 6 multiply 6 squared is 36 divided by 2. This is 36 divided by 2 is 18. Sorry. So 18, and this is 3 times 6, 18. So for n0 equal to 6, we will have that this expression is smaller than this one, and this is going to work, which is let me try to explain this a little bit more formally. Yeah. What we need this thing here to be bigger than that, okay? Because I want okay, usually I have all these things in my mind. I'm not doing algebra. I always have the intuition how to get there. So for this one, I don't. So let's forget about it. So, but anyway, if you apply algebra, you isolated the 3n, then you can figure out for which value of n squared this is going to be smaller. And yeah. I think That's it. Okay. So there are some exercise you can do right away. I don't know if the TA is there.
Yes, I'm here.
Okay, so can you do the exercise you have on hand for the big O notation?
Okay.
Yeah, thank you.
Okay, students, you have the presentation slide, do you? There are the exercises on big O notation. You should do that right now. And after 10 minutes, we'll check the answers. Okay? I hope that's okay. Okay, I think we should check the answers now. But first of all, can you see my screen? Uh-huh. You can see the screen, right? I suppose, yeah.
I see it at least.
Okay, that's good. So, does anyone have the answer for exercise 1.1? Well, which instruction can be used as elementary operation? Let me pick one. Hoàng Xuân Việt.
I think we can use the innermost for loop.
That's right. So can you give me the running time of this algorithm in terms of the number of times your selected elementary operation is executed?
The running time is n times n plus 1.
Yes. And the big O estimate for the running time of the algorithm.
Big O of n squared.
Okay, that's right. And what is computed and returned by this algorithm?
N times n plus 1.
You sure about that?
Yeah, I think it's the sum of all I from 1 to n, and then all j from 1 to n. So I calculate it as n times n plus 1.
Let me check that. Does anyone have another answer for question 1.4? I don't think that's n times n plus 1 per se.
I think it is n square multiply n plus 1.
Can you say that again?
N square multiply n plus 1.
N square. Yep. That is more reasonable. So can you explain your answer?
Can I explain on paper?
Yes, you can. You can scan your paper or share your screen or type in the chat. Any method you like.
It took me a minute.
Okay. Trần Khánh Lương and Hoàng Xuân Việt, each of you will get some bonus point and a high five. I say that. Perhaps when we can study offline, I'll give you your high five.
I have just upload my answer on the chat box.
Okay.
And you.
You all see Trần Khánh Lương answer, right? I hope so. Okay, so the algorithm will compute the total sum of I plus j, you can see. So what is the total sum of j's? You can see in the inner loop, j runs from 1 to n. So you have 1 plus 2 plus 3 plus 2n. And there are n loops like that. So that makes n times 1 plus 2 plus 3 to n. And the sum of the integers from 1 to n, you all have learned it is n times n plus 1 over 2. So the sum of all j is n squared times n plus 1 over 2. And the same can be applied to I here. So that make 2 times n squared times n plus 1 over 2, which is the answer. Do you all understand that? Or do I have to explain one more time? Hoàng Xuân Việt, you cool with that?
Yes, I see where I was wrong.
Okay, that's good. So we are done with exercise 1. Does anyone have any question before I move on to question 2?
Can you tell me again what is elementary operation of this exercise?
Okay, so the elementary operations should be the one that is executed the most when the algorithm run. So it should be this for loop here. But I can say that it will cause much confusion when we count the number of times this for loop is executed. In particular, you can argue over whether or not we should count the last execution of this operation, right? The one that breaks the loop. So from now on, you can choose whatever inside the loop as the elementary operation. Is only different by one execution. It wouldn't cause that much problem. And we are only interested in the big old time estimate here. So you can choose either the loop or whatever inside the loop. It's okay. Yeah.
So if I choose another elementary operation, so I will get another running time, which is not a problem.
You can choose another but it should be approximately the one with the highest number of execution per run. I guess.
Yes. Okay.
Does anyone have any other question? Or can we move on to exercise 2? I think we can move on. So exercise 2. Does anyone have the answers yet? Hoàng Anh Trung, can you
I
give?
think it's n multiply log n.
Okay, yep, that's right. And for F2?
It's n square.
Yeah. Okay, can you give the detailed answer for F1 and F2? Like, what is C and dot you chose?
In F1, I associate 3n and 3 log n 2 of n, and then I have 3n minus 3 multiply log 2 of n, and then I'm associate 9 time of n and 3. So I have the expression 3n minus 3 multiply log 2 of n and plus 9n minus 3 is all the way smaller than n log n. So I think this z function n is n log n.
Well, that's quite a handful. Can you write that down and upload your answer like Trần Khánh Lương did?
Okay. Wait me a second.
Okay. Thank you. 1 and 2. You give some bonus point. You get? Yeah. In the meantime, does anyone have the answer for F3 and F4? You can raise your hand or you can turn Trần Khánh Lương again. Okay. Yeah, Trần Khánh Lương.
I have done exercise 3.
Okay. What's your answer?
For n2 belong to big O n3, it is true because let's see.
Oh, I'm sorry. I mean the
F3.
part 3 and 4 of exercise 2. Not exercise 3 yet.
For F3, I choose n0 equal to 5 and C equal to 103. I can upload my answer.
Okay, thank you. That would be best.
Yes. Can you see my answer?
Yes. Everyone see Trần Cảnh Lương answer, right? Yes. So A not equal to equals 5, C equal 103. That seems correct to me. Okay. So for F4, can you give the answer for F4?
I just upload the answer.
Okay, thank you.
Can you see the answer of F4?
Yes, yes. Yeah, okay, that's right. So here's Hoàng Anh Trung answer. Okay, let me see. I don't quite understand this. Yeah, that's right, but yeah, that's okay. Everyone see Hoàng Anh Trung and Trần Khánh Lương answers, right? Do you have any question?
I have a question. When we find the GN, the big O of GN, we should we have to the Chung and Lung do before. I think we shouldn't just find the define the growth rate of the function when n goes to infinity.
Yes, that's right. Yeah, so yeah, you can find GN here, and F would be in the big O of GN. You just use the definition in the slide. This definition, here, use this. There are much more convenient tricks you can use. Professor Michel will teach you about that later. But for now, does anyone have any problem with exercise 2, or can we move on to exercise 3? I think we can move on. So here, who can give the answer of the first four question here on the left? You can raise your hands. Perhaps. Okay, Ngô Thị Thu Huyền.
Yes. For the first question, I say 2 because n to the n square always less than equal to n to the 3 as n greater than 1. And in this case, I choose CE1. So it exists C satisfying n square less than or equal to n to the 3.
Okay.
So 2.
Yep, that's right.
Yeah. For the second one is 2 because 2 to the n always less than 3 to the n as n greater than 1. So in this case, I choose C is 1. So C satisfies the requirement.
Okay.
The third one, I say false because as the second one, 2 to the n always less than 3 to the n as n greater than 1. So it doesn't exist C satisfying 3 to the n equal less than or equal to C time to the time C to time 2 to the n.
Okay.
Yeah, for the first one, can I post my picture of my solution because it's quite difficult to say.
Yes, you can upload your answer in the chat.
Yes.
You get some bonus point in your midterm exam. So in the meantime, who can give the answer for the last 4 questions here? On the right hand side, you can raise your hands. Let me see. Nguyễn Hoàng Tiến.
Yes. For the question E, I think the answer is false. And I will send you my proof on the message chat.
Okay.
For the question F, I think that the answer will be true because 2 to the power n plus 1 equal to 2 times 2 to the power of n. And this belongs to big O notation of 2 to the power n. For the question J, I think that the answer will be true because every function which belongs to the big O notation of 2 to the power n plus 1 will belong to the big O notation of 2 to the power n. And for the question H, I think the answer will be false because let's take a counter example, which is 3 to the power n. And according to the answer for the question C, to 3 to the power n not belong to big O notation of 2 to the power n, but 3 to the power n belong to big O notation of 3 to the power n. So the answer for the question will be false.
Yeah, that's right. You can give the answer in the chat for that one. Yeah.
Yes.
Okay, we have Ngô Thị Thu Huyền answer here. You can see that. Yes, very detailed, and this is the right answer. Thank you. You can use the answers given in the chart by these students as reference when you're having problem with this exercise. I hope that helps. Biết Hoàng Tiến. Đấy. Yeah, that's right. Huyền and Tiến get the correct answer. You can use that as a reference. So, did everyone understand question? I mean exercise 3. Do you have any problem here? I think now we can move on. So exercise 4. Who has the answer? Hoàng Trần Nhật Minh, right? You can give the answer, right?
So I will explain first, and I will upload my note. So
Okay.
this is the algorithm to find the kth smallest integer in an unordered list. So I will find the number of execution for the worst case of the second for loop, and then
Yes.
I will find the big O notation. It will be easy. So I think that's
Okay.
The execution times of the second for loop in the worst case is n squared minus n over 2. So the big O notation is n squared.
Wait, n squared minus n over 2. Can you re-explain that? Can you explain that again? I didn't catch it.
Wait for me for a minute.
Okay.
I have sent the picture of my work.
Okay, thank you. Let me see that. Chơi blah. Yeah, that sounds about right.
So if anyone needs further explain.
Oh, wait. In the worst case, yeah, you're right. Worst case, k equal to n.
Yes, because it's the case smallest number. So in the worst case, it will be the largest number of the array.
Yes, you're right. Do you all understand Nhật Minh answer? I will explain that here. So for this problem, the outer loop will always loop k times, and the inner loop always go from I plus 1 to n, because there is no, there's no condition that will break the loop early. So you can count them manually, like when I equal to 0, j equal to 1, run from 1 to n. So that gives, let me see, to n minus 1. Sorry. So that gives n minus 1 times of execution, and so on and so forth. And when I equal to k minus 1, you get n minus k times of execution, and you can take the sum of that, and it will be like Nhật Minh's answer. And in the worst case, you can see k should be the largest value of k should be n, because you cannot find the k plus 1 smallest integer in an array of k elements, right? So the answer here is good. That's correct. Do any of you have any problem with this exercise? No, really? Well, that's fast. So we can move on to exercise 5. Oh, the answer is here. But I think this is n to the power of 1 plus epsilon, because that's how math works, right? This one. Yeah. This is n to the power 1 plus epsilon, not 1 times epsilon here. Or even exercise 6 has the answers. So their answers are here. Do you have any question about that? No? Nobody has any problem with exercise 5 and 6? That's good. So the last exercise here, who has the answer? You can raise your hand. Yeah, Nguyễn Tống Minh.
Yeah, can you hear me?
Yes, okay.
So I will say that the result, I will say direct to the result. The result is for the polynomial expression, it will be n the n square plus 1, and all that time n. So the big O notation, in the big O notation, it will be O n power 3. Yes.
Yeah.
I will show my process of on the chat. Just wait.
Okay, thank you.
Okay, so are we done?
Wait. We're waiting for Dong Bing to give his answer.
Okay.
Sorry, because my internet is a bit lag, so
Yeah, it's okay.
maybe it's a bit slow. Yeah, so sorry.
Okay, so it's very interesting what you're doing. It is excellent. And I think the best way to learn this stuff is through exercise anyway. So I see some of you are pretty good in mathematics. So this topic should not be a big challenge to you guys. Okay, so while we are waiting for the solution, let me get back to to one question.
Vãi lồn máy lag à? Vãi! Chịu!
Okay, so when the student is ready, you just interrupt me and bring your answer. While you are preparing your answer, I can discuss a little bit about this question 1. So, question 1, if you really count the largest number of basic operation, it should be the for loop. Okay, so the for loop is execute, the inner for loop is execute n plus 1 time. So if you now count the total number of basic operations that are executed, the expression will be n plus 1 multiplied by n. So it's going to give you n squared plus n as an expression of the running time for this algorithm. On the other hand, if you count the assignment inside the inner for loop, the number of times this assignment is executed is n time. So if you count, if you want to come up with an expression that describes the running time of this algorithm, it will be n times n, which is n squared. So you get two expressions for the running time of the algorithm depending on which instruction you select to be the one that is executed the most often. One is n squared plus n, and the other one is n squared. But however, in terms of, since we select the dominant terms as an expression that they really that is describing the running time of an algorithm, they are both the same. So whether we count this instruction or this one, the running time is the same. So it is n squared, as we care only about the dominant term when we want to measure the complexity of the algorithm. However, in the slide of last week, introduction, sometimes I count, I'm not consistent about how I count the number of basic operations if I really want to get the one which is the one that is executed the most often. So if one student wants to come back to the slide on the PDF slide on introduction, and you can modify those, you can make it consistent, you can make this slide consistent by always counting the operation that is executed the most often. So you can use tools in PDF to highlight the place that you want to change, and then you can use the sticky note to make your change that you want to make. So for example, here it is which instruction. If I want to say, well, this is not correct and I want to replace this by which instruction, plural, then you can do this with the PDF. So this gives you a chance to have a contribution to the class note itself. So if somebody wants to change all the places that are not consistent in the introduction slide, you can do this and then send me the slide with your modifications. So I guess you can you all have a PDF reader. So I think our PDF reader now, you can use this function to highlight some text and then to indicate the modification using the sticky notes. Okay, so then the slide will be consistent with the choice of selecting the instruction that is executed the most often. At the end of the day, it doesn't matter, but it's always good to, when we say we select the instruction that is execute the most often, we really select this one. So in programming terms, this one is really executed one more time than this one to check the condition. Okay, so another thing we need to discuss, unless the student is ready with his solution. Not yet. Okay, another thing we need to discuss is what do you want for the final exam? Do you want 2 exams or 1 exam? Have you come up with some consensus on this question? No consensus? I have discussed this with the university, and the university required that you agree yourself with the form of the final exam. So that's why I give you this option, because look like we will have a final online. Hope not, but of course, if we have a final in class, if they change the rule and we are allowed to go in class, there will be only 1 final. But if we have the final online, you always have this option, but I have to have your agreement whether you want this or not. So I guess you have a representative in this class, so somebody is a representative of the class, so you can discuss with this person and decide what you want in case we have the final online, which of course I don't hope this will happen, but this epidemic is really difficult to predict, so we'll see. Okay, so oh, I have a solution. Okay, so somebody say that we all have agreed that we should have multiple final exams. So, okay, so you already decide. Great. So then it's going to be 2 exams, 2 final exams, about the same amount of time, each of them, on 2 different set of topics. And the grade for the first exam and the grade for the second final will be the same. So the total grade is 70% for the final. So the first final will be 35% and the second final will be 35%. Okay, so problem solved. So I will discuss now, I will confirm this with the university that if we have final exam online, this class will have 2 final exams. Excellent. I saw solution for question for this question that is excellent. So the person who wrote the solution for this one and prove it did a very good work. Okay. This is more detailed than what I did in this question, which showed that n again is always smaller than 1. Here the point is 1 point epsilon. Okay, so epsilon is between 0 and 1, so it is 1.2, 1.3, 1.4. So the point is not a multiplication, but the expression is expressed. This expression is a value greater than 1, greater or equal to 1, and smaller than 2. Okay, so we have discussed about the big O, and now I'm going to go quickly on big omega, on omega and theta. Again, the best way for you to learn this material is through exercise, and since you are pretty good in maths, that should be something that teach you a lot more than the theory. So the meaning of big omega, so to say that to define the big omega is a set of function, big omega of g. So it's a set of function fn such that they can be, the complexity can be bound below by gn. So we can find a constant c and a value n0 such that fn is always greater than c gn. So it's all the function fn that can be bound in this way that belong to omega of gn. So again, we have the function fn that is the running time of fn that is always greater than cgn. And we can prove this in 2 ways. We can decide that c is equal to 1, and then try to find the n0 such that fn is always greater than gn. So in this situation, we have to care about fn that have a negative term, okay? And to prove this, we need to find a value of n0. We have to find when this is larger than this, okay? So we have to find when the dominant term is larger than the negative term in the expression that describes the running time. So I want to show that this is bound below by n squared, but I have to worry about this value here. So for which value of n this is true? it is true when n is greater than 4. So since n is always an integer, so this is true when n is greater or equal to 5. Another way to prove that Fn is greater than Cgn is to assume that C is going to be smaller than 1 and find n0 that will make these two functions, will make this function smaller than Fn. So, or we can select a positive constant that is smaller than the dominant terms, but then we need to worry about the negative term. So let's look at this case where C, we assume that C is going to be smaller than 1, and we try to find n0, some n0, and we try to find some C for which this condition is going to be satisfied. So here I have n log n minus 2n plus 13. So I want to show that this is can be bound below by n log n. So n log n is the dominant term. So we don't need to care about this term, so we can get rid of it. But we need to care about the negative term. So I need to show that C n log n is going to be smaller than n log n minus 2n. So I need to find a C and n0 such that this is going to be satisfied. So if I isolate the C, I get this expression, 1 minus 2n log n, 2 log n, and I need to find a value of n such that this term here is smaller than 1, in which case I always have that part here that is positive, and that part being positive is going to be greater than this Fn here. This Fn term being positive is always going to be greater than n log n for some value of C. So we can choose, here I think I have choose n is equal to 8. So if n is equal to 8, this thing here is 2/3. 2/3 is smaller than 1. And 1 minus 2/3 is 1/3. So if C is equal to 1/3, I have C n log n is smaller than n log n minus 2n plus something. We could choose other value of n. So for example, if I choose n to be 16, so log in base 2 of 16 is 4. So this is going to be 1/4. One half, sorry. So 1 minus 1/2, it is, this is positive for any value, this is positive, the difference between the two is 1/2. So then I can select C to be equal to 1/2. And if I increase n, I can choose a C that is going to be greater. So the value of C depends on the value of n that we select, n0 that we select. This term here is going to get smaller and smaller as n increase. So if we start with n equal to 8, after that, if C equal to 1/3, after that, if we increase the value of n, this is going to be, this term is going to be smaller. So for any value of n that is greater than 8, this term is going to be positive, and we have this condition that is satisfied, C n log n smaller than n log n plus minus 2n plus 13. In this one, I select C to be a constant that is smaller than the constant of the fastest growing term. C, we select 1 here, so C is smaller than the fastest growing term. And we need to find again for which value of n this is true. So c is equal to 1, and I want this to be smaller than this expression. So removing n square on each side, so we get n 2n square minus 2n minus 7 is greater than 0 for value of n that is greater than 3. So for n equal to 3, this is minus 6, minus 13. Is for n equal to 3, this is 9, and it is 18. So for any value of n that is greater than 3, this expression is going to be greater than 0. If I select n to be equal to 2, this is 8, and this is 4 and 7, so it is minus 11, so that's not true. So selecting 1 or selecting a value of, selecting 1, yes, to be the constant, or selecting any constant that is smaller than the dominant terms, we need then to select the value of n0 that will satisfy the inequality. So this is not very challenging, so you can guess that you can assume that c is going to be smaller than 1, and then try to find an n0 that make this inequality, make this term positive, and then you select c for that with respect to this. For theta is you combine omega and you combine the big O. So for theta, you need to find two constants, C1 and C2, such that Fn is greater than C1 Gn and smaller than C2 Gn, but for a same N0. Okay, so the only difficulty here is that we have to have the same N0 that work for both C1 and C2. Normally, we first select C1 and the N0 that is going to work with this, and then we try to find a C2 that will work with the N0. So theta means that we have a bounding function that is sandwiches between, we have the function that we try to bound that is sandwiches between C2 Gn, the upper bound, and C1 Gn, the lower bound. For any value of n that is greater than n0, the function fn is not larger than this, and it's not smaller than this one. So it's always stronger to be able to prove that a function is in theta of something, so that the running time of a function is in theta of something. It's always a stronger result than upper bound or lower bound. But for some function, it is not possible to find this. So here we have an example. And I select C1 to be 1 over 2. So if C1 is 1 over 2, for which value of n, this is going to be smaller than n squared. So I need to have this term here to be greater than 5n. So I have to have a value of n that will make this thing greater than 5n. So since my constant here is 1 over 2, this thing here has to be greater than 5n because I have select C1 to be 1 over 2. So this is true for which value of n? Certainly not true for n equal to 2. So n equal to 2, this is 4 divided by 2, and this is 10, so it's not working. But eventually it's going to work. So for n equal to 10, we have this term here that is going to be greater than this one. So for n equal to 10, this function is 50, and for n equal to 10, this is 50 also. And if I increase n to 11, so this is going to be 122. divided by 2, so this is 61, and this is greater than 60. So as n increase, the value, this term is getting larger and larger than this one, so it means that this function is always going to be, this expression is always going to be larger than this one. Now that we have satisfied the lower bound, so we have found C1 and N0 that make this function smaller than G1, Gn. We need to find another constant C2 that works with N0 that is equal to 10. So what we want this term here to be smaller than n squared. Okay, so we have n squared minus we have n squared minus 5n. So we need to have this term here that is negative to be smaller than this thing here, to make sure that this expression is always greater than n squared. So we need to find a value of C such that C times 10 square is going to be larger than 5n. So I have n squared smaller than 5n. This work for C2 that is equal to 1. Let's see if this is correct. So if C2 is equal to 1 and n is equal to 10, so this is 100 minus 50 plus 7, 57. And this thing here is 100, so 57 is smaller than 100. And if I increase the value of n, this term here always get larger. So for n equal to 11, this is 122 minus 56 plus 7, so it is 61, and this is 122. So the idea again is the only difficulty with data is to deal with the selection of the constant C2 when the N0 is already fixed. Last, so there is another example. I will skip this and let you the chance to do more exercise. Last, for those of you who are familiar with the limit rules, you can also prove the relationship between Fn and Gn using the limit rule. So if you calculate the limit of the growth rate of the function, the running time of the function and its growth rate, so the relationship between these two, and this convert to some constant L, it means that Fn is bound exactly by Gn, above and below. Okay, so the constant here, you can make this constant smaller for Gn, so to make Gn smaller than Fn, and you can make this constant greater than for Fn to bound the constant, to bound Gn, to bound Fn. Sorry, we make a constant larger than L to bound Gn. So this is going to be your constant to make Gn bigger than Fn. So if the limit of the relationship between Fn and Gn converge to some constant L, then you have the proof that Fn is in theta of Gn. Of course, you have to use the limit rule to prove convergence of this relationship, this ratio to some constant. So if you are familiar with the application of the limit rule, you can use this to prove this kind of relationship. If the limit of Fn to Gn, so that means if Fn is greater than Gn, the limit of this is going to converge to 0. So if you can prove that this relationship converges to 0 in the limit of n, then you have a proof that Fn is in omega of Gn, so Fn is bound above by Gn. On the other hand, if Fn, if this limit grows to converge to infinity, so that means Gn is greater than Fn. So definitely Fn is not in Gn, okay? But Gn is in big O of Fn, so Gn is smaller than Fn. In that case, we can say that Fn is greater than Gn for some constant. So this is another way that you can use to prove the complexity or to prove that Fn is in some class, some complexity class. Okay. Okay, so I have an easy lecture today. I will let you do some exercise. So now you need to prove the relationship between Fn and Gn using the technique that has been described previously. So we can go on depending on whether you want to break or not. So Kwong, you can start again driving the exercise.
Okay. So I think we'll have 10 minutes break and then another 10 minutes for you to begin doing the exercises. So yeah, see you in 20 minutes, I suppose.
Okay, that worked for me.